Hi everybody. So we're going to talk about section 5.2, which is logarithmic functions. There's two different types of problems that we're going to do in this section. First, we're going to talk about graphing logarithms, okay, and we're going to use base graphs and transformations, and then we'll talk about solving logarithmic equations, okay? So let's look at the features of the graphs of logs. Okay, so there's a key feature, okay, which is a vertical line on the y-axis, okay, which the graph does not cross. Okay, this is specifically y equals log base b of x. Okay, so the base graph type graphs. Okay. Okay, then there are three key points. Okay, so our key points are 1 over b, comma, negative 1, 1, 0, and b, comma, 1. Okay, if those key points look familiar to you, they should. These are the key points from the exponential graphs, but with x and y reversed, right? So if you've been watching the videos about inverse functions, you'll know why these are reversed, okay? And if you haven't been watching those videos, I encourage you to. All right, so let's look at a base graph. Okay, so we'll graph y equals log base 2 of x. Okay, so our key points are going to be 1 over 2, right, because b is 2 in this example, so we'll have 1 over 2, negative 1. Then we'll have 1, 0, okay, and then we'll have b, which is 2, 1. Okay, so now we're going to use that to draw our graph. Okay, now I know you guys haven't seen the shape of these before, so I'll show you what the shape looks like, but we are going to draw our key points. So okay, so 1/2, negative 1, 1, 0, and 2, 1. Okay, and the shape looks like this. Okay, so that's what our shape looks like. All right, and all logarithmic graphs have this basic shape. Okay, let's do one more base graph. Okay, and then we're going to use this graph to do some graph transformations. Okay, so our key points are 1 over b, which is 1 over 3, negative 1, okay, 1, 0, and b, which is 3, comma, 1. Okay, so there's our key points. Okay, so we have our vertical line here on the y-axis that the graph doesn't cross. Then we have 1/3, negative 1, 1, 0, and 3, 1. Okay, and then it's going to have that same shape. Okay. All right, so now that we have this base graph, let's use it to do some transformations. Okay. Okay, so there's this negative sign. We know that means reflect. okay? And because it's inside the functions, we're going to reflect the x coordinates, okay, which is going to be across the y-axis. Okay, so let's look at what our graph is going to look like. Okay, so the dotted line is still along the y-axis. Okay, now our point that was at 1/3 -1, we're going to reflect it across. Our point that was at 1, 0 reflects across, and our point that was at 3, 1 is going to reflect across. Okay, and then you'll see that the whole shape of this graph is facing backwards. Okay, so you can compare that to the original graph, right, and see that it's reflected across that way. Okay, let's look at another transformation. Okay, so we have this +1 inside the graph, so we know that's going to affect the x coordinates. Okay, because it's inside. All right, and because it's +1, we know we're going to move left 1. Okay, so let's look at our graph. Okay. Okay, so we're going to move our dotted line from 0 to -1 because we're moving it left 1. Okay, we're going to move the point that was at 1/3 -1 left 1, the point that was here left 1, and the point that was at 3, 1 left 1. Okay, and this is what my new graph will look like. Okay. All right, a couple more transformations. We're always using the same base graph here, so that's why we know what the original key points are. Oops, that's a transformation we just did. There we go. All right, so now we have this +2 outside, so this is going to move it up 2. Okay, so okay, we still have our dotted line. Okay, so this point is going to move from 1/3 -1 up 1, 2. This point is going to move up 1, 2. And this point from 3, 1 is going to move up 1, 2. Okay, and we'll have our graph that looks like this. Okay. Now the last transformation I want to look at is the one that's arguably the hardest. Okay. Okay, the stretching. So this is going to stretch the graph times 2. Okay, so it should look, this is vertical. Okay, so it should look taller and skinnier than the base graph. Okay, so we're still going to have our dotted line here. Okay, so our x coordinates are going to be the same, so we're still going to have 1/3, but then instead of -1, we're going to multiply the y coordinate by 2. So -1 times 2 is -2. So this, our new point, is going to be 1/3 -2. Okay, then here we'll have our y coordinate, which is 0 times 2, that's still 0. okay? And then here from 3, 1, we'll have 3 and then multiply the y coordinate by 2. So we have the point 3, 2. Okay? And our graph would look like that. Okay? So if you do compare this to the base graph, right, you can see how flat this graph is, okay, and this one is much more vertical. Okay? So that's what you do to graph logs. You graph the base graph, okay, and then you use the transformations. All right, let's look at solving some log equations. Okay. Okay, so the first thing you want to do is isolate the log. Okay, so if there's only one, isolate it. If there's more than one, get them together on one side. Okay, now the second thing, now you might not always need to do this, okay, is use the log properties to combine into a single log. Okay, now this is one of the applications of the log properties, right? When you're solving these equations, you need them to combine the logs into one log. Okay, then you're going to change to exponential form. Okay, and then you're going to finish solving normally. Okay, and then the very last thing, and this should be familiar to you guys from when we talked about square root type equations, is you're going to check for extraneous solutions. Okay, all right, so let's look at an example. Okay, so the log is already isolated. There's only a single log. Okay, so the kind of preparatory steps where you get it ready to change to exponential form are already done. Now we're going to change it to exponential form, so the base of the log becomes the base of the exponent. Okay, remember a log is an exponent, so this is the exponent here, and then the x is the answer. Okay, so 4 cubed is 64. Okay, we're finished solving for x. Okay, and what you're checking for, okay, is that you're not plugging in 0 or negatives to the log. Okay, so that's what you're checking for when you're checking for extraneous solutions. So if you look at 64, you would plug it in here. It's positive, it's not 0, so that's great. All right, so this really is a solution to our equation. All right, let's look at a slightly more difficult example. Okay, so the first thing we want to do is isolate this log. Okay, so I'm going to subtract 5. Okay, and then I'm going to divide both sides by 3. Okay, once I have a single log isolated on one side, I'm going to go ahead and change to exponential form. Okay, and this gives me the solution x equals 7. Now, I'm going to look at my original equation and say, am I allowed to plug in 7 here? Yes, because it's positive, it's not 0, so this is a solution to my equation. Okay. Let's look at another example like that one. Okay, so again, the first thing I'm going to do is isolate this log, not that. Okay, so I'm going to subtract 7. And then I'm going to divide both sides by 3. Okay, now I have a single log isolated on one side, so I'm going to change to exponential form. Okay, 2 cubed is 8. Okay, and this problem has one additional step where I need to subtract 3 from both sides. Okay, now I'm going to check that when I plug this in, I'm not going to get a negative here. Okay, so 5 plus 3, that's 8. It's not negative, it's not 0, so this is a solution to my equation. Okay, all right. One more example like this. Okay, I want to isolate my log, so I'm going to subtract 2. Okay, and then I'm going to divide both sides by 4. Okay, now I have a single log isolated on one side, so I'm going to change to exponential form. Okay, 5 squared is 25. Okay, and now to isolate x, I need to subtract 2 from both sides and divide both sides by -1. Okay, so you might be thinking, oh, this is a negative number, I can't plug that into the log. But look at the original equation. Okay, you have 2 minus x. Okay, so if you were to plug this in, right, 2 minus -23, that's the same as 2 plus 23, or 25. Okay, so you are allowed to plug this in. This is okay. All right, so that means this is really a solution to our equation. All right, so even though the answer is negative, right, the number that you're plugging into the log overall, 25, is a positive number. Okay, all right, let's see one more type of log equations that can come up before we talk about using the log properties. Okay, so in this example, the variable is actually the base of the log, but the process for solving these is exactly the same. Okay, so you're going to isolate the log by itself. It is isolated, and there's only a single log. Then we're going to change to exponential form. Okay, and then now to solve this, we need to take the square root of both sides. Okay. Now, here's one case where you do have an extraneous solution. Okay, b squared equals 16 does have two solutions, +4 and -4. But we know that the base for a log has to be a positive number. Okay, so for us, Okay, this is an extraneous solution. Okay, and this is our real solution, b equals positive 4. Okay, let's look at another example where the variable is in the base. Okay, we're going to change to exponential form. Right, and now to get rid of the cube, we need the cube root. Cube root of b cubed is b, cube root of 125 is 5. So we have a single solution, it's positive, so we know that's a good solution. Okay, let's look at one more like this. Okay, so the first thing I'm going to do is subtract 1 from both sides. Okay, and then I'm going to divide both sides by 4. Remember, we're doing this because we always want to isolate our log. Okay, now that we have it isolated, we're going to switch to exponential form. Okay, and we solved these types of equations before. These are called power equations, right? So remember, this is the same as the 4th root of b cubed. Okay, we can get rid of the cube by cube rooting both sides. Okay, the cube and the cube root are going to cancel, so I'll just get the 4th root of b. Okay, and the cube root of 8 is 2. Now to get rid of the 4th root, I have to 4th power both sides. Okay, these two are going to cancel, and I get 2 to the 4th, which is 16. Okay. All right. Let's talk about what happens when you need to use the log properties. Okay, so now we have the two logs together on one side and everything else on the other side, so that's a good start. Okay, now we want to combine these two using the log properties. So remember, when you add two logs, that's the same as multiplying the inside part or the argument. Okay, and now we want to change to exponential form. So at this point you might be thinking, well, there's no base here. Remember, log without a base is really log base 10. Okay, so this would be 10 cubed equals 2x. 10 cubed is 1,000. And then we would divide both sides by 2. Oops. 500. Okay. We're going to check if we're able to plug that in. Plug it in, 500, which is a positive number. So that's our actual solution, x equals 500. It's not extraneous. Okay, let's see another equation like that. Oops. Okay, so we have log base 10 of x plus 3 plus log base 10 of x equals 1. Okay, so we're going to combine these using the log rules. Okay. And now I'm actually going to go ahead and multiply this out. Okay, now that I've simplified using my log properties, I'm going to change to exponential form. So remember the base is 10. So I'd have 10 to the 1 power equals x squared plus 3x. Okay, and 10 to the 1 power is 10. Okay, this is a quadratic, so I'm going to move everything to one side and try to factor. So this does factor x plus 5, x minus 2, and that gives me two solutions, -5 and +2. Okay, so when you check those, are you allowed to plug in -5 here? You'd have -5 plus 3, that's -2. So no, we're not allowed to. So this is extraneous. Okay, and x equals 2 is our real solution here. All right. Okay. So if we're going to solve this equation, we need to combine them. Now remember, when they're subtracted, that's the same as dividing the arguments. Okay. And now that we have a single log isolated, we're going to change to exponential form. So 3 the base, 3 the exponent equals x minus 2 over x plus 1. Okay, 3 cubed is 27. All right, and now I'm going to use cross multiplying to solve this. So 27 times x plus 1 equals 1 times x minus 2. Okay, so I'm going to subtract x from both sides. And then subtract 27 from both sides. And that gives me x equals -29 over 26. Okay. Now the question is, am I allowed to plug this in? So when I check, okay, okay, the very first term that I plug this into from the original equation, I don't even have to compute this to know that this is going to be negative. Okay, so this is bad. This is an extraneous solution. Okay, so that means there are no solutions. Okay, if your only candidate solution turns out to be extraneous, that means there's no solutions to your equation. Let's go over one more like that. Okay, so we're going to combine these using the log properties. Okay, then we're going to change to exponential form. Oops. All right, 8 to the 1 power is 8. Now we're going to multiply both sides by 2 and subtract 5 from both sides. We're going to check if we're allowed to plug this in. 11 plus 5, that's 16, that's positive. This is always a positive number. Okay, so this is really a solution. It's not extraneous. Okay, I hope that makes sense, and I'll see you guys soon.